All right, let's jump right in. Have you ever really thought about what happens in that split second after you flip a light switch? Today, we are pulling back the curtain on the invisible force that powers, well, pretty much everything, electric current. We all use it, but how does it actually work? Let's get into it.
So it all starts with a puzzle, one you've probably never even thought about. You flip a switch on the wall, and a light bulb way across the room turns on, instantly. But how? How is that even possible? To figure out this bit of everyday magic, we need to meet our main character, the electron.
Okay, now get ready for this, because this is where it gets weird. The actual speed of a single electron drifting down a copper wire is just 0.07 millimeters per second. That is ridiculously slow. A snail could beat it in a race. So if the electrons are just crawling along, how on earth does the light turn on instantly? This is the paradox we need to solve.
To solve this mystery, we first have to understand what the heck these electrons are actually doing inside the wire before you even touch the switch.
So, inside a copper wire, when there's no power, you've got billions of free electrons just bouncing around like a crazy, chaotic mob. They're going every which way, bumping into each other, there's no overall flow. But the second you connect a battery, something amazing happens. They all get the same memo and start to drift in the same general direction. And that ordered march, that unified drift of charges, is what we call electric current. It's not just random motion, it's a net flow of charge in one direction. We even have a way to measure it. The current, I, is just the amount of charge, Q, that flows past a point in a certain amount of time, T.
And here it is, the solution to our slow electron paradox. When you flip that switch, you're not sending one single electron on an epic journey all the way to the light bulb. No way. Instead, you're creating an electric field that travels through the entire wire at nearly the speed of light. Think of it like a command that's instantly broadcast to all the electrons at once, including the ones already waiting inside the bulb's filament. They all start moving at the same time. It's like a chain of dominoes. You tip the first one, and the last one falls almost immediately. That's why the light comes on so fast.
Okay, so we know this electric field is the boss, telling all the electrons to move. But what creates that field? What's giving it the big push to get the whole thing started in the first place? Let's look at the driving force behind it all.
Well, that push has a name, potential difference. But you and I, we usually just call it voltage. The best way to think about it is like water pressure in a hose. If there's no pressure, the water just sits there, right? But if you crank up the pressure, you get a powerful flow. In a circuit, voltage is that electrical pressure that shoves the electrons and makes them move.
So where's this pressure coming from in, say, a battery? It's actually some pretty cool chemistry. A chemical reaction inside acts like a tiny pump, separating positive and negative charges and piling them up on two different terminals. This separation creates that potential difference, that voltage, just waiting to push electrons through whatever you connect to it.
All right, so you'd think with all this push, the electrons would have a clear shot, right? A nice, smooth highway to travel down? Well, not exactly. It's actually a lot more like a chaotic obstacle course.
Picture this. As our little electron tries to zoom through the wire, it's constantly smashing into the huge, fixed atoms of the metal itself. This turns its path into a chaotic zigzag. It gets a push from the field, moves a tiny bit, then bam! It collides, loses some steam, gets another push, and on and on. This constant obstruction is just a part of life for an electron in a wire.
And that constant bumping and blocking? That has a name. It's called resistance. Every single material has some level of resistance. Things like copper have super low resistance, which is why they're great conductors. And then you have stuff like rubber with crazy high resistance, which is why we use it as an insulator to keep us safe.
So what makes something more or less resistive? Well, it pretty much boils down to four main things. First, the material itself is huge. Copper is an open freeway, while rubber is a total dead end. Second, length. A longer wire has more resistance, just because there's more stuff to bump into. Third, thickness. A thicker wire has less resistance because there are more lanes for the electrons to travel in. And finally, temperature. For most metals, the hotter they get, the more their atoms vibrate, and the more they get in the way, increasing resistance.
So let's recap. We've got the push, that's voltage. We've got the flow, that's current. And we've got the roadblock, that's resistance. And you know what's really cool? There's a super simple, elegant rule that ties them all together.
And here it is. Ohm's law. V equals I times R. It is the golden rule of basic electricity.
This simple formula describes the relationship between voltage, current, and resistance. And it's incredibly powerful because if you know any two of those things, you can always figure out the third.
But here's a little twist. Ohm's law, well, it's not really a law in the way gravity is. It's more of a strong suggestion that some materials follow. Materials that follow it, like a simple wire, are called ohmic, and the relationship between voltage and current is a nice, predictable straight line. But a lot of modern electronics, like LEDs, are non-ohmic. Their resistance actually changes as the voltage changes, giving them this curved graph.
Okay, this isn't just theory. Understanding this stuff is literally a matter of life and death. Let's talk about circuits, shocks, and how to stay safe. So let me ask you a classic question. What's the real danger in an electric shock? Is it the high voltage or is it the high current?
You might think it's the big, scary voltage number, but it's the current. It's always the current. Voltage provides the push, sure, but it's the amount of current that actually flows through your body that causes the damage. And look at how little it takes. We're talking about fractions of an amp. Just 70 thousandths of an amp, if it goes through your heart, is likely fatal.
This whole idea of reliability and safety is exactly why your house is wired the way it is, using parallel circuits. You know those old cheap holiday lights where if one bulb goes out, the whole string dies? Oh, so frustrating. That's a series circuit, one single path. In a parallel circuit, like in your home, there are multiple branches. So if your lamp burns out, your TV and your fridge keep right on working. It just makes sense.
All right, let's wrap this up by solving a classic riddle, using everything we've just learned. We've all seen it, birds sitting happily on massive high-voltage power lines. Why don't they get zapped?
And the answer brings everything we've talked about full circle. To get a current to flow, you need a potential difference. You need a voltage. Since both of the bird's feet are on the exact same wire, there's practically zero voltage difference between them. No voltage difference means no push. No push means no dangerous current flows through the bird. Simple as that, it's a perfect real-world example of how these invisible forces work.